is Emmanuel Salazar, and I would like to present my project that is called Autonomous Car Displacement with Differential Equations. My objective is to use differential equations to enable the car robot to move autonomously from its current position to a specified goal. The specific job that the differential equations have in this task is the sequential computation of movements that will allow the car to turn towards the direction of the goal. I would like to start with what is an autonomous mode. The development of robots that are humanly controlled has been conquered in many areas. Current research is focused on the development of autonomous robots capable to make decisions to perform a specific task successfully. The branch of the computer science that studies the designs of this type of robot is called artificial intelligence. The task of making an autonomous car robot includes identifying obstacles, finding the shortest path, and generating a sequence of instructions to get to the desired goal. One of the most known autonomous modes is the Google car, which is a self-driving car. The computation required to move the car from its current position to a specific goal is divided into two stages. The first stage takes care of the car turning to be aligned with the goal, and the second stage will take care of calculating the missing distance to move the car in a straight direction. This dynamical system of equations describe the motion of the car in order to get to a desired location. The theta in the third equation defines how much the car will rotate in order to make a turn. These equations are not coupled, meaning that one could be solved separately as three unrelated initial value problems. First, I tried to solve the system of differential equations explicitly, but I encountered some problems. The solutions had too many unknowns, but my results contained some constants. I just found one constant out of the three, and the rest of the function was too complex to be solved explicitly. Then, I recurred to solve the system numerically, and Mathematica uses the Runge-Kutta method, and when I plug the equations in, it allowed me to see how they behave. For example, when the linear velocity is equal to 3 centimeters per second, and starting from the origin and letting the theta be equal to 0, we could move the robot in a straight direction. When time is greater than 1 and theta is equal to pi, we could move the robot in circles, but when the time is equal to 1, we could almost complete one circle. When the theta is equal to negative pi, we'll go in the opposite direction. So we're going to use shorter intervals to be able to make turns and manipulate the car. So now the question is, how do I make the robot go from one point to another? If the goal is placed at phi 7, I will rotate the car to the right to align it with the goal. By using the Runge-Kutta method, we will move in short intervals, knowing the position and the angle that it makes with the goal. When the difference of angle is equal to 0, we will recalculate the missing distance, and we will move the robot in a straight direction till we get to the goal. This Runge-Kutta method is very useful because if the wheels slide and the robot fails to accomplish the desired distance on the small interval, then the robot can regenerate the path to make the next movement. Now that we know how the system of differential equations behave, we could use them to convey commands to the robot. With the advancements that I made, the next step will be to implement the Runge-Kutta method to solve the differential equations in real time in the Arduino system. Some of the applications of this autonomous robot is that it could go through small spaces, taking the place of human lives to look for victims in fallen buildings. I hope you like it, and thank you for watching.